drop a glass. Watch it shatter on the floor. Pieces fly everywhere. Water splashes across the tiles. And in an instant, order becomes chaos. Now ask yourself a simple question. Why doesn't it ever happen in reverse? You have never seen shattered glass leap off the floor, reassemble itself, and land intact on the table. You have never seen spilled coffee flow upward into a cup. You have never seen a scrambled egg unscramble itself back into yolk and white. These events don't happen. They can't happen. Something forbids them. But here's the strange part. The laws of physics don't forbid them. Newton's laws work perfectly well in reverse. Maxwell's equations for electromagnetism are symmetric in time. Quantum mechanics, at its most fundamental level, doesn't care which direction time flows. If you filmed two particles colliding and played the film backward, the physics would still be valid. Every fundamental equation we know allows time to run in either direction. So why does it only run one way? This is the mystery of the arrow of time. And after 50 years of thinking about it, I can tell you that it remains one of the deepest unsolved problems in all of physics. We know there's an arrow. We can describe it mathematically, but we cannot fully explain where it comes from. Today I want to take you through everything we understand about why time has a direction, and more importantly, everything we don't understand. Because this isn't just a physics problem, it's a question about the nature of reality itself, about why the past is different from the future, about why we remember yesterday but not tomorrow, about why we age and die and cannot reverse the process. The arrow of time rules your entire existence, and we still don't know why it points the way it does. Let's start with thermodynamics. In the 1800s, physicists studying heat and energy discovered something profound. They found a law that actually does distinguish past from future, a law that isn't symmetric in time. The second law of thermodynamics. The second law says that in any isolated system, entropy tends to increase over time. Entropy is a measure of disorder, or more precisely, a measure of the number of microscopic arrangements consistent with what you observe macroscopically. High entropy means many possible arrangements. Low entropy means few. A neat room has low entropy. There's only one way for everything to be perfectly organized. A messy room has high entropy. There are countless ways for things to be scattered around. The second law says that systems naturally evolve from low entropy to high entropy, from order to disorder, from special to typical. This is why your room gets messy if you don't clean it. This is why ice melts in warm water. This is why hot coffee cools down. And this, physicists believe, is the arrow of time. The direction of time is the direction in which entropy increases. The past is the direction of lower entropy. The future is the direction of higher entropy. We remember the past because memory formation increases entropy. We cannot remember the future because that would require entropy to decrease. This seems like a complete answer. The second law explains everything. Time has a direction because entropy has a direction. But wait, there's a problem. A deep, fundamental problem that has troubled physicists for over a century. The second law is not a fundamental law. It's a statistical law. It emerges from probability, not from the basic equations of physics. Let me explain what I mean. Imagine a box divided in half by a partition. On one side, there's gas. On the other side, vacuum. You remove the partition. What happens? The gas expands to fill the whole box. Entropy increases. This is the second law in action. But here's the thing. Every individual gas molecule obeys Newton's laws. And Newton's laws are time reversible. If you could somehow reverse the velocity of every single molecule at some instant, they would all retrace their paths and end up back on one side of the box. Entropy would decrease. The second law would be violated. This is not impossible, it's just extraordinarily unlikely. The reason entropy increases is not that the laws forbid decrease. It's that there are vastly more high entropy configurations than low entropy configurations. If you start with gas on one side and let it evolve randomly, it will almost certainly end up spread throughout the box, simply because there are so many more ways to be spread out than to be concentrated. But almost certainly is not certainly. In principle, entropy could decrease. In principle, the gas could spontaneously collect on one side. In principle, the broken glass could reassemble itself. It's just that the probability of this happening is so unimaginably small. that it would take longer than the age of the universe to occur even once. So we never see it. For all practical purposes, entropy always increases. This is the statistical explanation of the arrow of time. Time has a direction because we happen to live in a universe where entropy is increasing. The arrow points from less probable configurations to more probable configurations. But this explanation has a fatal flaw. If the laws of physics are time-symmetric and the second law is just statistics, then the arrow of time should point in both directions from any given moment. Think about it. If low entropy evolving to high entropy is overwhelmingly likely, then high entropy evolving to low entropy in the past should be equally overwhelmingly likely. If you see a half-melted ice cube in a glass of water right now, statistics says it probably came from a more disordered state in the past, not a more ordered state. In other words, if you only use the second law and the time-symmetric laws of physics, you would predict that the past had higher entropy than the present, just as the future will have higher entropy than the present. But that's obviously wrong. The past had lower entropy. The ice cube came from a freezer where it was fully frozen. The universe came from the Big Bang, which was an extraordinarily low entropy state. So where does the arrow actually come from? The answer, unsatisfying as it is, comes down to initial conditions. The universe started in a very special, very low entropy state, and it's been increasing in entropy ever since. The arrow of time points away from that special beginning. This is called the past hypothesis, the hypothesis that the early universe had extremely low entropy, and that's why entropy has been increasing ever since, and that's why time has a direction. But this just pushes the question back. Why did the universe start in such a low entropy state? Why were the initial conditions so special? We don't know. This is one of the deepest mysteries in physics. We can describe the Big Bang. We can calculate what the early universe looked like. We can measure the cosmic microwave background radiation and confirm that the early universe was remarkably uniform and hot. But we cannot explain why it started that way. The arrow of time exists because of a brute fact about the initial conditions of the universe, and that brute fact remains unexplained. Entropy is not disorder in the everyday sense. A messy room is not a high-entropy system in the thermodynamics sense. Entropy is about information. It's about how much you don't know about the microscopic details of a system when you only know its macroscopic properties. Ludwig Boltzmann, the great 19th century physicist, gave us the equation that defines entropy. S equals K log W. Entropy equals Boltzmann's constant times the logarithm of W, where W is the number of microscopic configurations consistent with the macroscopic state. If you have a gas at a certain temperature and pressure, there are many possible arrangements of the individual molecules that would give you that same temperature and pressure. The more arrangements, the higher the entropy. This definition connects entropy to information. High entropy means you're ignorant about the microscopic details. Low entropy means you know more. The system is more constrained. There are fewer possibilities. From this perspective, the second law says that information tends to get lost. The universe forgets its microscopic details. Distinctions that existed in the past get washed out, averaged over, irretrievable. This is profound. The arrow of time is the direction in which information is lost. The past is knowable because it left records, traces, memories. The future is unknowable because the information about it doesn't exist yet. But wait, doesn't quantum mechanics say that information is never truly lost? Doesn't unitarity, the principle that quantum evolution preserves information, contradict this? Yes and no. At the fundamental level, information is preserved. The quantum state of the universe evolves unitarily. Nothing is truly destroyed. But practically, information gets scrambled beyond recovery. It gets spread out across so many degrees of freedom that no realistic measurement could ever retrieve it. This is the difference between fundamental physics and thermodynamics. Fundamentally, nothing is lost. Practically everything is lost. And the practical loss is what defines the arrow of time. Why do we remember the past but not the future? This seems obvious. The past has already happened, so we can remember it. The future hasn't happened yet, so we can't. But this answer is circular. It assumes the very distinction between past and future that we're trying to explain. The real answer involves entropy. Memories are physical structures. When you remember something, your brain contains a physical record of that event. Neurons are connected in certain patterns. Chemicals are distributed in certain ways. This physical record is a low-entropy structure. It contains information. For a memory to form, entropy must increase. The process of recording information always generates heat, always increases disorder somewhere. Writing information into a memory requires energy dissipation. This is why we remember the past. Memory formation is an entropy-increasing process, and entropy increases toward the future. We remember the direction of lower entropy, which we call the past. Could we remember the future? In principle, if entropy were decreasing, memory formation would work in reverse. We would have records of the future instead of the past. But entropy isn't decreasing. The past hypothesis guarantees that entropy increases toward the future. So our memories point backward, toward the low entropy direction. This is strange to think about. Your sense of time, your feeling that the past is fixed and the future is open, your entire experience of the flow of time, all of this emerges from entropy. It's not built into the fundamental laws. It's a consequence of the initial conditions of the universe. If the universe had started in a high entropy state, or if entropy were decreasing, your experience of time would be completely different. You might remember the future and not the past, or you might have no sense of temporal direction at all. The arrow of time is not a feature of reality itself. It's a feature of our particular universe with its particular initial conditions. Where is all this heading? If entropy always increases, what happens when entropy reaches its maximum? When there are no more low entropy reserves to tap, no more gradients to exploit, no more order to degrade? This is the heat death of the universe. The final state of maximum entropy, where everything is uniform, everything is at the same temperature, and nothing ever changes. In the heat death, there is no arrow of time. Without entropy increase, there's no direction. Past and future become indistinguishable. The universe reaches equilibrium and stays there forever. This sounds bleak. The ultimate fate of everything is cold, dark, featureless uniformity. All the stars burn out. All the black holes evaporate. All the structures decay. In the end, nothing remains but a thin haze of particles at near absolute zero, drifting forever in an infinite void. Is this depressing? Some people think so. The universe ends not with a bang, but with a whimper, with the slow erasure of everything that ever existed. But I'm not sure we should see it that way. The heat death is not nothing. It's equilibrium. It's peace. It's the end of change, yes, but also the end of suffering, the end of decay, the end of loss. You could see it as the universe finally coming to rest after billions of years of activity, and more importantly, the heat death is unimaginably far away. We're talking about time scales of 10 to the power of 100 years or more, far longer than any human can comprehend. The universe has plenty of time left for stars to form, for life to flourish, for consciousness to explore and wonder. The arrow of time rules the present. It gives us change, growth, experience, meaning. Without the arrow, without entropy increase, nothing would ever happen. The heat death is the price we pay for having a universe where things happen at all. Here's something that puzzled physicists for a long time. If entropy always increases, if the universe tends toward disorder, how does life exist? Life is highly ordered. Organisms are fantastically complex structures, far more organized than random arrangements of atoms. How can complexity arise in a universe that tends toward disorder? The answer is that life doesn't violate the second law. Life increases entropy overall while creating local pockets of order. When you eat food, you're taking in low-entropy chemical energy. Your body uses that energy to maintain its structure, to grow, to reproduce. But in the process, you generate heat. You excrete waste. You increase entropy in your environment more than you decrease it internally. Life is an entropy-exporting machine. It creates order locally by exporting disorder elsewhere. The total entropy of the system, you plus your environment, always increases. The second law is never violated. This is beautiful when you think about it. Life exists because of the arrow of time, not despite it. The flow from low entropy to high entropy is what makes energy gradients possible, and energy gradients are what life exploits. Without the arrow of time, without entropy increase, there would be no energy to harness, no gradients to exploit, no thermodynamic possibility of life at all. We exist because the universe started in a low entropy state and has been increasing in entropy ever since. The arrow of time is not our enemy. It's the condition that makes us possible. But of course, the arrow of time also kills us. Aging is entropy. Your body accumulates damage over time. DNA gets corrupted. Proteins misfold. Cells lose their ability to repair themselves. Eventually, the system fails. You die. Death is the victory of entropy over the local order that was your body. The complex structure that was you dissolves back into simpler components. Your atoms disperse. The information that defined you gets scrambled beyond recovery. Is this sad? Of course. I don't pretend otherwise. We don't want to die. We love life and we fear its end. But the same arrow that kills us is the arrow that gave us life. The same entropy increase that degrades our bodies is the entropy increase that powered our metabolism. We cannot have one without the other. Every moment of consciousness is a thermodynamic event. Neurons firing, consuming energy, generating heat, increasing entropy. To think is to degrade. To live is to decay. We burn through our low entropy reserves moment by moment, experiencing time as we do so. When the reserves run out, we stop. That's death. Not a failure of the universe, but the natural consequence of the very processes that made us alive. I find a strange peace in this. The arrow of time is not cruel, it's not personal. It's just the direction in which things happen. And happening is all we have. Let's be honest about what we don't understand about time. We have no solid explanation for why the universe began in a state of low entropy. We just assume it did, but we don't know why. Was it a quantum gravity effect? A transition from an even earlier state? Or maybe it was just chance, one possibility in a vast multiverse, and we just happened to live in the one where life could form. Some even think the arrow of time is fundamental, not something to be explained. After decades of study, I've learned to live with this uncertainty. We also don't fully grasp how different arrows of time connect. The expansion of the universe, the flow of our memories, the link between cause and effect. Are they all just different faces of entropy? Most physicists think so, but it's not proven. It's a huge, active area of research. And what about consciousness? Physics describes a static universe, yet we experience a flowing present. Where does this feeling come from? Why does now feel special? These are profound, open questions at the heart of physics. Thanks for watching. I want to leave you with something other than mystery and uncertainty. The arrow of time is strange. It emerges from symmetric laws plus asymmetric initial conditions. It creates a profound difference between past and future that isn't written into the fundamental equations. It makes change possible, makes life possible, makes consciousness possible, but it's also beautiful. Without the arrow, nothing would ever happen. The universe would be static, eternal, unchanging. There would be no stories because stories require time. There would be no meaning because meaning requires change. There would be no experience because experience requires a direction, a flow, a movement from state to state. The arrow of time is what gives the universe a narrative, a beginning, a middle, an end, the low entropy past, the increasing entropy present, the high entropy future. This is the shape of existence. We are temporary patterns in this flow, brief eddies of order in the river of entropy. We arise, we persist, we dissolve. The arrow carries us along whether we understand it or not. I've spent my life trying to understand it. And what I've learned is that understanding doesn't diminish the wonder. The arrow of time is just as mysterious now as it was when I first encountered it. But the mystery is beautiful. It's the mystery of why anything happens at all. Drop a glass, watch it shatter. Feel the moment passing, never to return. That's the arrow of time. That's the deep asymmetry that rules your life. And that's physics at its most profound. Not just describing what happens, but touching on why there is a direction to happening at all. We don't have all the answers. Maybe we never will. But the question itself is worth asking. Why does time only move forward? Because the universe began. Because entropy was low. Because the initial conditions were special in a way we cannot yet explain. And because of that we exist. We remember. We experience. We wonder. The arrow points one way, and in that direction lies everything we know.